Alright, welcome to lesson 5.09. Here we're going to be writing exponential functions given a verbal description of a situation. This is important because when someone describes something to you, you want to be able to put it into a mathematical form that allows you to then make further sense of it. Let's get started. So let's start with this situation right here. Company A, the value V sub A in dollars of an investment T years from 2002 is given by this formula here. At company B, the value V sub B in dollars of a similar investment T years from 2002 is given by this formula that I've written down here. What I want you to do is decide which investment is a better investment and to explain why. So pause the video and try to do that on your own, and if you need a guiding question, take a look at what I've written down here. Once you've figured it out and it written down your reasoning, go ahead and press play and we'll talk briefly about it. So let's start off with this. The initial value of both the investments is $2,000. That's not hard to see. We can tell that because when t is 0, which is the year 2002, both of these investments, V sub A and V sub B, are equivalent to 2,000. The question then becomes, what happens as the years start ticking along? One of the nice questions to ask is, how long will it take each investment to double? And the reason I ask this is because we notice that the base of each investment is 2, which means that over some period of time, we're going to multiply by 2, which causes our investment to double. Let's start with company A. By observing the exponential statement here, how many years must go by for us to multiply by 2, or for our investment to double? Think about it this way. When t is 0, we're in year 2002, our exponent is 0. In order for us to then multiply by 2, our exponent needs to go from 0 to 1. 2 to the 1 represents a multiplication of 2. Well, if t just goes to 1, our exponent will be 1/5, and that will be 2 to the 1/5. That's not quite what we're looking for. For my exponent to be equal to 1, t has to be equal to 5, because 5 divided by 5 is 1. So it's only when t is equivalent to 5, or after 5 years, that for a company A, we will actually have 2 to the first power and multiply by 2. So for company A, our investment will double every 5 years. Now, that is some really important information. That helps you understand what's happening. Another way to view the investment is to rewrite our exponential form here so that we have t by itself. This will allow us to see what the growth rate is each year. So I encourage you to do that here. We discussed that yesterday. Let's take a look now at company B. Let's transition now to company B. Let's think about the exact same scenario. We start when t is 0 in 2002, and at that point our exponent is 0. What will t have to become in order for our exponent to be equal to 1 so that we multiply by just 2 and double our investment? Well, if we increase t all the way to 1, it means 1 year has gone by, our exponent will actually be 5, which is too big. 5 times 1 is certainly not 1. But what could we multiply 5 by that would give us 1? In other words, what I'm asking is 5 times what equals 1? Well, that's exactly the reciprocal of 5, which is 1/5. So when t is equivalent to 1/5, then I will have 2 to the 1, 2 to the first power, which will double my investment. So notice I don't even have to wait a whole year, I just have to wait 1/5 of a year. Okay, let's read this statement. We're saying that the investment doubles every 1/5 of a year. Now, I don't know about you, but if I asked someone how frequently something occurs and they told me every 1/5 of a year, I would think that was a little strange, right? We're not normally going to talk about fifths of a year. We'd want to translate that into something that makes a little more sense, which is months. So if you have 12 months, what's 1/5 of that? Well, that's actually not too hard. We're going to take the 12 months, and to take 1/5 of it, we're going to multiply by 1 over 5, which gives us 12 over 5. And taking 12 and dividing by 5 gives us 2 and 2/5, which is 2.4, or 2.4 months. So instead of writing doubles every 1/5 of a year, I actually want to say that this doubles every 2.4 months, which we have now written here. I encourage you, if you're curious, to write this in terms of months and days. So in other words, finding out what 0.4 out of 30 or 31 would be. But for our purposes, 2.4 months will be just fine in clearly identifying how often that investment doubles. Now, what I want us to take away from this discovery problem is how a description in words is translated into the mathematical function. Clearly, the initial value is easy to see here, but if I told you something doubled every 5 years, you might not guess that I could write it as 2 to the t over 5. What I want to think about is when I hear it doubles every 5 years, well, doubling is multiplying by 2, and every 5 years means I need the exponent to change by 1 every time t increases by 5. So that's going to give me an exponent of t over 5 because that will only go to 1 once t becomes 5. Similarly, if I'm told it doubles every 1/5 of a year, or 2.4 months, I know that I need the exponent to only be equivalent to 1 after t has gotten to 1/5 of a year. And so I need an exponent of 5 times t, because only when t is 1/5 will 5 times 1/5 then give me 1, so that I'm multiplying by 2. You'll get the hang of this the more you work with it, but I encourage you to make sure you have these written down nice and neat so you can refer back to it. Let's go ahead and take these down in a couple of key points. So you might have been wondering, how do I actually tell that I should write an exponential model, particularly if they don't tell me it should be an exponential model? And this is an important one that people tend to forget. An exponential model is appropriate when a quantity is increasing or decreasing by a fixed percentage, right? That's the way that we write the expression. When we're multiplying by something, we're changing it by a percentage of itself, which is this either growth or decay rate that we've written down here. So whenever you see a fixed percentage increase or decrease, you want to go ahead and use an exponential model. When you're creating this model, there are a couple things. The first is look for an initial value. That is, on most cases, but not all, going to be what the a value happens to be, the leading coefficient. Next, you want to determine the growth rate. So you're looking for it doubles every 5 years, or it increases by 3% every year. For example, if I said it increased by 3% every year, let's say its initial value was 10, so I'd have 10 times increasing by 3% every year would be 1 plus 0.03 to the t power, since it increases by 3% every year. If I said it increases by 3% every maybe 2 years, I'd want to have t over 2 so that I didn't multiply by 1.03 until I had t increase by 2. So make sure that if your growth rate is not given per single unit of time, as I just explained, if it increased by 3% every 2 years, you'd want to adjust your function accordingly. And then you can go ahead and write it in this form. So if this is how I've got my function, I can rewrite it as 10 times 1.03, and I can raise 1.03 to the 1/2 and then to the t power. This allows me to get a more easy to explain growth rate in terms of per year. So 1.03 to the 1/2 is going to be 1.015, and so I can rewrite this as 10 times 1.015 to the t power. And I can really see without rewriting it in this form that I am increasing by 1.5% every single year. All right, I'm going to go ahead and give you a couple of problems to try and make sure that you have got some solutions when you show up to class tomorrow. All right, so here are the 3. I actually think these go in order of difficulty. So trying number 1, you should be able to get that. Number 2 ramps it up a little bit, but you've actually seen an example pretty similar to this, so you should be okay. And then number 3 requires you to incorporate something called half-life here. And I want to point out, if you have taken a chemistry class or a biology class, you've probably heard this term. Half-life refers to how long it takes for the amount of something to get cut in half. So keep that in mind when you go through and answer these questions. Make sure that you've got solutions ready to go for tomorrow.